Tonight's topic is parameters of a transmission line, and we'll start off with inductance. Electric transmission line has 4 parameters affecting its ability to fulfill the function as part of the power system. That are resistance, inductance, capacitance, and conductance. Conductance exists between conductors and ground, which accounts for leakage current at the insulators of overhead lines and through the insulation of cables. Since leakage at insulators is negligible, the conductance between the lines is also negligible. Some of the properties of an electric circuit can be explained by the electric and magnetic fields accompanying its current flow. Any variation in the current in the conductor causes a change in the number of lines of magnetic flux linking the circuit. Any change in the flux linkages induce a voltage in the circuit proportional to the flux rate of change. This is all basic stuff that you've done in Engineering 1. The inductance of a circuit relates to the voltage induced by the changing flux to the rate of change of the current. Capacitance exists between the conductors and is defined as the charge on the conductor per unit of potential difference between them. The resistance and inductance, uniformly distributed along the line, form the series impedance. Capacitance of a transmission line is the result of the potential difference between the conductors. In the early days, conductors were usually made of copper, but aluminium has replaced the copper due to a lower cost and lighter weight per meter. Due to the larger diameter of aluminium, the flux line will be further apart and the lower voltage gradient will be less likely to produce corona. Symbols identifying different types of aluminium conductors: AAC, all aluminium conductors; AAC, all aluminium alloy conductors. And then we have ACSR, aluminium conductor steel reinforced, and ACAR, aluminium conductor alloy reinforced. And now you all know the resistance of a transmission line conductors is the most important cause of power loss in a transmission line. The term resistance means effective resistance unless otherwise stated, and R is equal to the power loss divided by the square of the current, and that is equal to rho L over A, where rho is the resistivity of the conductor, L is the length, and A is the cross-sectional area of the conductor. The change of resistance with temperature, R1 over R2, R1 over R2 is T plus T2 divided by T plus T1, where R1 and R2 is the resistance at temperatures T1 and T2. T is the constant in degrees Celsius from the graph, is 234.5 for annealed copper with 100% conductivity, 241 for hard-drawn copper at 37.3% conductivity, and 228 for hard-drawn aluminium of 61% conductivity. Now let's look at the series impedance of a transmission line. The inductance of a transmission line is calculated as the flux linkages per ampere. For a constant permeability, the flux linkages can be expressed as L is equal to lambda divided by I. To obtain an accurate value for the inductance of a line, it's necessary to consider the flux inside each conductor as well as the outside flux. Now let's look at this drawing. We have a conductor there, and the radius is r, and at a certain distance away from it there's a small annular circle with a diameter of dx and a small area ds. By Ampere's law, the MMF around any closed circuit path is equal to the net current enclosed by the path. Therefore, the MMF is equal to the integral of h dot ds, and that is equal to I, where h is the magnetic field intensity, ampere turns per meter, s is the distance along the path, and I is the current enclosed. At any point x, we have that MMF is equal to the integral of hx dot ds, and that is equal to Ix. And the distance 2 pi x times hx is Ix. And then if we assume a uniform current density, Ix is pi x squared over pi r squared times the current. So that's just the ratio. Now if we substitute it back for hx, we obtain that hx is equal to x divided by 2 pi r times I. The flux density x meters from the center of the conductor is Bx is mu hx, which is equal to mu x times I divided by 2 pi r squared. In the tubular element of thickness dx, the flux d phi is Bx times the cross-sectional area of the element normal to the flux lines, the area being dx times the actual length. So there we have the equation. D phi is equal to mu xi over 2 pi r squared times dx. Now if you integrate, the flux linkages d lambda per meter length, which is caused by the flux in the tubular element, are the product of the flux per meter length and the fraction of the current linked. Thus, d lambda is equal to pi x squared over pi r squared d phi, and that is equal to mu I x cubed over 2 pi r4 to the power of 4. Now let's look at that drawing again. Point P1 and point P2, and a small increment in the radius there. Integrating from the center of the conductor to the outside edge to find the internal lambda, the actual flux linkage inside the conductor we obtain. Can we get rid of this? Okay, that's probably better, yeah. So lambda internal is the integral from 0 to t mu I x cubed over 2 pi r cubed dx. And if we integrate that with respect to x, we get mu I over 8 pi. Now for a relative permeability of 1, which is mu is equal to 4 pi times 10 to the power of minus 7, lambda internal becomes a half times 10 to the power of minus 7. And the internal inductance is a half times 10 to the minus 7 henries per meter. Now let us derive an expression for the flux linkages of an isolated conductor due only to a portion of the external flux, which lies between D1 and D2 from the center of the conductor. P1 and P2 are such points in this figure. So then again we say 2 pi x, hx is I, bx is mu I over 2 pi x, and the flux d phi in the tubular element of the thickness is d phi is mu I over 2 pi x dx. The flux linkages d phi, d lambda per meter are numerically equal to the flux d phi, since flux external to the conductor links all the current in the conductors only once. So between P1 and P2 the flux linkages are lambda internal is from P1 to P2 d phi dx, and that gives us mu I over 2 pi ln d2 over d1. And lambda 1, 2 is 2 times 10 to the power minus 7 times I ln d2 over d1. Okay, that proof you must know by heart. So let's look at the inductance of a single phase 2 wire. Adding the inductance due to the inner and external flux linkages, we have L1 is a half plus 2 ln d over R1. By replacing R1 by R1 ln e to the power minus 1/4 and equating that to R1 dash. Now this is due to the effect of the current flowing only on the outside of the conductor. Skin effect. So L1 is 2 times 10 minus 7 ln d over R1 dash. And thus for a double line, L is equal to 4 times 10 minus 7 ln d over R dash. Now if we look at the inductance of a composite conductor, that is a difficult formula there. Is the 2 times 10 minus 7 times the ln of the mnth root of all of that divided by the n squared root of that at the bottom. Now the top part, the mnth root, is known as the geometric mean distance between conductors x and y, and that is also equal to dm. Then the n squared root is equal to the self gmd, which is equal to ds. So let's look at example 1. One circuit of a single phase transmission line is composed of 3 solid 0.25 centimeter radius wires. The return circuit is composed of 2.5 centimeter radius wires arranged as below. The distance between those conductors is 6 meters, and the distance between the one circuit and the other circuit is 9 meters. So now we have to estimate the inductance due to current in each side of the line and the inductance of the complete line. So dm between sides x and y. So dm is the mnth root of dAd, dAc, dBd, dBc, dCd, and dCe. So those are the distance that's A, B, and C. So that's DE. So that is DAD, and then the distance DAE, and then BD times BE, and CD times CE. I doesn't want to go back. So DAD is equal to DBE, which is 9 meters. And then DAE is equal to dBD and dCE. And that is the square root of 6 squared plus 9 squared, which gives us the square root of 117, which is 10.81. So therefore dm is the m, which is 3, times n, which is 2. So therefore that gives us the 6th root of 9 squared times 15 squared times 15 times 10.817. And that gives us 10.74 meters. Then the Sx will be the nth root of DAA, and then DAB and DAC, and then again DBA, DBC, and CC, and then from C to B and C to A. So that's all the distances between the conductors doubled. And again, DAA is the self in GMR of the conductor, which is 0.778, which is e to the power minus 1/4 times the radius times the distance is 6 and 6 and then 12. Double up. Always you will see it's from A to B and B to A, and from B to C and C to B, and then from A to C and from C to A. And therefore that gives us a value of 0.481. And then for side Y, we've only got 2 conductors, so that is n squared, and it's 0.778 times 0.5, which is this radius, times the distance between each of them is 6 meters. Therefore, that is 0.153. So L is 2 times 10 minus 7 ln D over, that is dm over ds, and that gives us a value of 6.212 and times 10 minus 7 henries. Then y is 2 times 10 minus 7, the same distance, 10.74 for ds, and 0.153, which is dsy. And that gives us 8.5, and the sum of the two inductances will give us L, the total inductance, which is Lx plus Ly, which gives us 14.71 times 10 to the minus 7 henries per meter. Okay, the inductance of three-phase lines with spacing. La is 2 times 10 minus 7 ln D equivalent over ds. D equivalent, as you've done in distribution 3, is the difference or the distance between that is D11, D23, and D13. The cube root of, that gives us the equivalent distance of the conductors. So, let's look at the inductance for bundled conductors. For a 2-strand bundle, ds for the bundle is the square root of ds times d. That should be d. The distance between the conductors. Then for a 3-strand bundle is dsb cubed, and then you've guessed correctly, for a 4-strand it will be dsb the cube root of ds cubed. But there's something wrong there. That should be times 1,09. Okay. Now determine dsb for the following bundle in terms of its radius. So there we have 3 conductors, radius r, and if we use first principles, ds of the bundle is n squared daa, which is the self GMR of the first conductor, then the distance from A to B and A to C, and then self GMR of B and the distances to A and C, and then the self GMR of C times the distance from C to A and C to B. Self GMR is 0.7788 R. There are 1, 2, 3 of them. And then the distance from A to B. Let's assume they're all touching. So that will be 2R and 2R and back. So there's 4 of them. And then from there to there is 4R. And it's back and forth. Therefore, if we calculate everything there, we get to 1.7037 R. Now what does that mean? That if we replace those 3 conductors by 1 conductor, it would have the radius of 1.703 of one of those radiuses. Alright, let's try another one. For the next bundle in terms of the radius. So, we have 2R from there to there, from there to there, from that conductor to that one, and to that one there. And that distance there, that will be, according to Pythagoras, 2R squared plus 2R squared square root. Okay, let's see. So that will be n squared of the distances from the self distance of each one of them, self GMR, and then the distance from A to B, A to C, and A to D for all of them. And therefore that we have 0.778 R to the cube. 2R, there's 8 of them. Remember, it's from A to B and A to C and A to D, back and forth. And then 2R squared plus 2R squared is 2 square root 3 R. So therefore, if we calculate it, we get 1.723 R. Now let's look at the 3-phase bundle conductor. Consider the following 2-bundle 3-phase system. There we have the 1 phase, the 2nd phase, and the 3rd phase. The radius of the conductors are 0.25. They are 6 meters apart, and the distance between the conductors is 0.45 meters. And we have to estimate the inductance per kilometer. So because it's a 2-bundle system, ds for the bundle is going to be ds times d, which is 0.778 times 0.25 times 0.45, and that gives us 29.6 times 10 to the power of minus 3. And the equivalent distance of the 3 phases is the cube root of 6 times 12, which gives us 7.5595. And XL is 2 pi times 50, which is the frequency, times L, which is 2 times minus 7, ln D equivalent over ds, 2 times pi times 50, 7.595 divided by 29.6 times minus 3, and that gives us 348 microhenry. Then the next parameter that we are going to have a look at is capacitance. Now, shunt admittance of a transmission line. The basis for analysis of capacitance is Gauss' law for electric fields. It states that the total electric charge within a closed surface equals the total electric flux emerging from that surface. The lines of electric force originate from the positive charges and terminate on the negative charges. Charge density normal to a surface is denoted dF. Now, normal to a surface means it's perpendicular to that surface. So it's going straight through the surface. And it equals Ke, where K is the permittivity of the material surrounding the surface, and E is the field electric intensity. If a long straight cylinder conductor lies in a uniform medium such as air and is isolated from other charges so that the charge is uniformly distributed around the periphery, the flux is radial. That means if we have a long straight conductor, all the flux lines is radial to that conductor. The electric flux density x meters from the conductor can be computed by imagining a cylindrical surface concentric with the conductor x meters in radius. Since all parts of the surface are equidistant from the conductor, the cylindrical surface is an equipotential surface, and the electric flux density on the surface is equal to the flux leaving the conductor per meter length divided by the area of the surface in an actual length of 1 meter. Okay, equidistant means it is the same distance anywhere from the line. Equipotential means the potential is the same all over. So the electric flux density is dF, and that is Q divided by 2 pi x, coulombs per meter, where Q is the charge on the conductor in coulombs per meter, and x is the distance away from the conductor where the electric flux density is calculated. You remember this stuff from S1, Engineering 1? Probably too long ago. The electric field intensity, or the negative of the potential gradient, is equal to the electric field density divided by the permittivity of the medium. E is equal to Q over 2 pi xk. Potential difference between 2 points due to a charge. This is defined as the work done in joules per coulomb necessary to move a coulomb of charge between 2 points. The electric field intensity is a measure of force on a charge in the field. The electric field intensity in volt per meter is equal to the force in newtons per coulomb on a coulomb of charge at the point considered. Between 2 points, the line integral of the force in newtons acting on a coulomb of positive charge is the work done on moving the charge from a lower potential to the point of higher potential, and is numerical equal to the potential difference between the 2 points. So let's look at a long straight conductor carrying a positive charge of Q coulombs per meter. There's the path, distance, D1 to the point P1. There's the charge, D2, is that distance from the conductor to the outer perimeter, which is P2. Positive charge on the wire will exert a repelling force on a positive charge placed in the field. For this reason, and because D2 is greater than D1, work must be done on a positive charge to move it from point P to P1. And P1 is at a higher potential than P2. The difference in potential is the amount of work done per coulomb of charge moved. On the other hand, if the 1 coulomb of charge moves from P1 to P2, it expends energy, and the amount of work of energy in Newton meter is the drop from P1 to P2. And remember, the potential difference is independent of the path followed. The simplest way to compute the voltage drop between 2 points is to compute the voltage between two equipotential surfaces passing through P1 and P2 by integrating the field intensity over a radial path between the equipotential surfaces. So V12 is the integral from D1 to D2 of E dx, and we replace E by Q over 2 pi kx dx, and if we differentiate it with respect to dx, we get Q over 2 pi k ln D2 over D1 volts. Note that the volt drop between 2 points may be positive or negative depending on whether the charge causing the potential difference is positive or negative, or whether the volt drop is calculated from a point near the conductor to a point further away, or vice versa. Let's look at the capacitance of a two-wire. Capacitance between the conductors of a two-wire line is defined as the charge on the conductor per unit of potential difference between them. So C is equal to Q over V, farads per meter. By the principle of superposition, the volt drop from the conductor to conductor B due to the charge on both conductors is the sum of the volt drops caused by each charge alone. So VAB is QA divided by 2 pi k ln D over RA plus QB 2 pk ln D over RB. So that is the voltage across those 2 points. And since QA is equal to minus QB, because the one line conductor is positive, the other one is negative, VAB can be expressed as QA over 2 pi k ln D squared over RA times RB. Capacitance. CAB is QA over VAB, and we substitute the values, and then we get T 2 pi k over ln D squared over RA over RB. And if RA is equal to RB is equal to R, then CAB is 2 pi k over ln D over R. Okay, if the line is applied by a transformer having a grounded center tap, the potential difference between each conductor and ground is half the potential between the conductors, and the capacitance to ground or neutral is Cn or CAN is equal to 2 pi k ln D over R, farads per meter to neutral. If we go to a three-phase line with equilateral spacing, the equation for the two lines are given. VAB is 1 over 2 pi k QA ln D over R plus QB ln R over D. And if we now look at conductor C, the charge on it is QC, and VAB is QC over 2 pi k ln D over D. And if we consider all the charges together, we get VAB is equal to 1 over 2 pi k QA ln D over R plus QB ln R over D plus QC ln D over D. And the same for VAC. And if we add those two, we get VAB plus VAC is 3QA over 2 pi k ln D over R. and VAN is then divided by 3, and it is QA over 2 pi K ln D over R volts. And the capacitance is Q over V, and therefore it's 2 pi K divided by ln D over R, farad per meter to neutral. Now, charging current is applied to the current associated with the capacitance of a line. So for a single phase line, I charging is J omega CAB times VAB. And for a 3-phase line, J omega CN times VAN. Now let's look at unsymmetrical spacing, where A is in position 1, B in position 2, and C in 3. Then we get that equation that VAB is QA ln D1 over 2, D1 over R plus QB ln R over D12 plus QC ln D2 3 over D31. And now if we change the position of A, we get that, and we change the again to in position 3, that will be the equation. As said before, the equivalent distance, cube root of D12 times D13 times D23. Unsymmetrical spacing, then we have VAB is I over 2 pi, 1 over 2 pi K QA ln D equivalent over R plus QB ln R over D equivalent. VAC is that. 3 VAN is VAB plus VC. And because QA plus QB plus QC is equal to 0, we get that 3 VAN is equal to 3 over 2 pi K times QA ln D equivalent over R, and the capacitance is 2 pi K over ln D equivalent over R. Now, do you think I've bored you with this? But only to get you to know the theory behind this. So, if we go to the capacitance for calculation for bundled conductors, 2 bundle, square root RD, 3 bundle, cube root of RD squared, 4 stranded bundle, 1,09 cube root, fourth root of RD cubed. And capacitance is 2 pi K ln DE equivalent over DSC. Now let's look at that example that we did previously of the 2 conductors. So DSC will be 0.25 times 0.45. Remember, there is no 0.7788 now because we are working with capacitance and it's just between the 2 lines. That gives us 33.54 times 10 minus 3 meters. Equivalent stays the same as 7.559. And C is equal to 2 pi K divided by ln D equivalent over D of the bundle. And that gives us 14.574 times 10 to the power minus 7 farads per meter. And that brings us to the end of this lecture.